Hello everybody, what's good? I hope you're doing okay in this time. My name is Petrus Regar, a PhD candidate in Department of Chemistry in Chungyun Christian University in Taiwan. Today I would like to explain my work about freshwater shrimp as aquatic invertebrate model to evaluate the non-targeted pesticide induced toxicity by investigating their physiologic and biochemical parameters. This work already been published in Antioxidant, so I hope you can read it in there. Crop is our source of main food like rice, wheat, and in order to increase this main source of food, a lot of farmers will use the pesticide. And imidacloprid is one of the most used pesticide in the world, especially in Taiwan. Imidacloprid is a neonicotinoid pesticide that block nicotinic acetylcholine receptor in insect. Why is this pesticide used a lot in farm? Because has a high efficacy against a broad spectrum of insects. This pesticide work by act on nicotinic acetylcholine receptor in nervous system and causing dysregulation of neurotransmission or cholinergic synapses that will lead to overstimulation, tremors, paralysis, and ultimately will cause death. Actually, this pesticide is much more toxic to insect than to vertebrate. Even though this imidacloprid is a good pesticide that can increase our source of food, however, a lot of farmers will abuse the use of this pesticide, and in the end, it can contaminate our ecosystem, like our soil ecosystem and the aquatic ecosystem. Especially in aquatic ecosystem, it will affect our aquatic animal. Even though in the start I said that this one quite specific, more toxic to insect, a lot of study has been done that this imidacloprid actually can affect non-target animal such as aquatic animal. And one of that is the freshwater shrimp. This shrimp actually a good trichotoxicity vertebrate model. A lot of study already done that this animal is actually a good model for the ecotoxicity. While the possibility of neonicotinoid pesticide exposure exists in both targeted and non-targeted animals, as I said before, but there is still a limited data about imidacloprid toxicity on the non-targeted animal, especially in aquatic animal. So, because of that, we want to examine the imidacloprid possible acute effect on complex behavioral activity and neurotoxicity using biochemical, molecular biology, and also computational techniques like molecular docking in freshwater shrimp such as Neonicardinea denticulata as an aquatic animal model. This is the overview of our work. So first we will expose the imidacloprid to the freshwater shrimp, and after that for every day until day 3 we will test the locomotion test of the treated fish, and after that on day 4 we will test the heart and gill measurement, and also we will sacrifice the shrimp for the biochemical test. And for the rescue test, first we will expose the shrimp in imidacloprid for 24 hours. After that we will move the fish to the acetylcholine and also to the normal freshwater and check their locomotion activity for 3 days, I mean. And after that we will check the heart and gill ventilation and to compare it with the treated imidacloprid shrimp. This one is already been done before in the shrimp. Actually this one is like just a preliminary data. After we expose the shrimp with imidacloprid, you can see here some of the shrimp cannot move and cannot swim. Just a little bit of shrimp that will move. And this is our work. as you can see here, the control is moved really fast, really robust, a lot. They are moved a lot, while the treated stream with imidacloprid, as you can see, just stay. Even this one look like that, only a little bit. Even on the lowest concentration, it already can reduce the locomotion activity compared to the control one. As we can see here, this is the locomotion of the control, and this is the locomotion of treated stream. They are not moving a lot compared to the control one. And here is the data. As you can see here, the control is really high, the locomotion activity, while for the treated stream it did not show any movement at all, or the movement is really low compared to the control one. As you can see here, it is significantly lower compared to the control one. And we also check the heartbeat and gill ventilation of the treated fish and the treated shrimp. You can see here, the mandible is moved slower in this one, and actually the heartbeat also slower compared to the control one. We can see it again. So we check the biomarker expression after we treated the shrimp with the imidacloprid, and we can see here, from all the biomarker we test, there are no significant difference from this. We suppose that imidacloprid effect on locomotor and heartbeat seems likely not be caused by changes in the biomarker, but by other mechanisms. So that is why we tried the rescue experiment by use acetylcholine administration to rescue the heartbeat and gill ventilation in shrimp. In here we can see it is really short that become normal. At first the heartbeat and gill ventilation is lower, significantly lower to the compared to the control one, but after that it is really not, at day 2 both of them become similar compared to the control one, and at day 3 ultimately the heartbeat is similar, and the gill ventilation also did not show any differences. So we can conclude from here the administration of acetylcholine can rescue the heartbeat and gill ventilation. And this one is the acetylcholine effect, just the acetylcholine effect. Actually for the heartbeat it can increase the activity heartbeat compared to the control. So it is makes sense, because in here the lower at day 0 after exposure to imidacloprid it is lower, but after the administration of acetylcholine it is become higher and normal. And this is the acetylcholine exposure rescue on the locomotion activity. As we can see, after imidacloprid exposure it is really low compared to the control one, but after that the higher concentration we can see here, the 1 ppm did not show any differences. So which means that the 1 ppm can rescue the acetylcholine the treated shrimp. So because of that we check the binding affinity of the imidacloprid to the nicotinic acetylcholine, and this one already done by our collaborator in Philippines. In here the nicotinic they show that imidacloprid has a superior binding affinity to nicotinic acetylcholine receptor, so that is why they can affect the locomotion activity and the heartbeat and gill movement by binding with the nicotinic acetylcholine receptor and cause the reduce of locomotion activity. So this is the conclusion and our proposed model. Actually the imidacloprid will bind with the nicotinic acetylcholine receptor and will reduce the locomotion activity, gill ventilation and heartbeat. And from the acetylcholine receptor we find that because acetylcholine and imidacloprid will bind with the nicotinic acetylcholine receptor, the use of acetylcholine receptor will prevent the imidacloprid to bind with nicotinic acetylcholine receptor, and in the end it will be increase, or the locomotion activity, gel ventilation, and heartbeat rate will become normal because we rescue the stream with acetylcholine. So thank you for listening. That's all from me. Thank you.